Hello, everybody, ladies, gentlemen, and of course, non-binary. I'm Amelia Thompson, and joining me today is Landon Gerdes. He's a design engineer specialist in Watertown, South Dakota, which is where we are headquartered. Now, during today's topic, there are a lot of precautions and steps that need to be taken in order to create a custom transformer. But today's webinar is focused on transformer design but with a consideration for safety. Currently, I am hosting today's webinar from the comfort of my couch while I heal up from a hamstring surgery. Apparently, during our last webinar, somebody told me to break a leg, and I take my job very seriously. Just kidding. I'm done making that joke. Won't make it anymore. Hopefully, I am back at the office next week because we have a very full schedule. On Tuesday, we have our next power webinar with ST Microelectronics. This is joint webinar with Wurth Elektronik and ST. It's migration to USB-C, meeting EMC standard, effective power protection, and high interoperability. Again, that's on Tuesday. And then on Wednesday, Wurth Elektronik's own Frank Puhani returns to present a behind-the-scenes look at current sense resistors. You can register online at www.we-online.com/webinars or look for the invitation emails. I believe they are being sent out probably on Friday and then on Monday. So you can click those links to get registered. Now, if you have any questions during today's webinar, feel free to ask them in that questions box. I see that we had a couple coming in. I do see some comments. I appreciate all the well wishes. Thank you very much. If your questions don't get answered or you think of them later, if you need any help with your transformer design, we got you covered. Just email us at hereforyou@we-online.com. As a reminder, because you registered for today's webinar, you will automatically receive the presentation slides and the video on demand when they become available. Give us a day or so, 24 to 48 hours. Just look for the link in your email. And of course, all of our webinars are made possible thanks to our exclusive sponsors right next door in Minnesota, Digikey Electronics. I also want to mention that if you can't get enough of me, and I know you can't, then you can hear me every single week with our new podcast. Each week, I am bringing application notes, blogs, press releases, and our webinars to an audio format. The Wurth Elektronik What's Up Radio podcast, available on all podcast streaming networks, including Spotify, iTunes, Google Podcasts, anywhere. So if you like listening to podcasts, check out our What's Up Radio podcast. Now let's begin today's Wurth Elektroniks webinar with Landon Gerdes presenting Transformers. How does safety affect your design?
Yes, thanks, Amelia. And hello, everyone. I appreciate you taking time out of your schedule to join my presentation. As Amelia mentioned, my name is Landon Gerdes, and I will be your presenter today on the topic of custom transformers. More specifically, we'll dive deeper into the safety requirements from the transformer perspective, and then discuss how these safety requirements affect the transformer, focusing mostly on the areas of performance, size, and the ever-important topic of cost. Before we begin the presentation, though, I'd like to give you just a quick introduction of myself. Again, my name is Landon Gerdes. I graduated from South Dakota State University in 2010 with my bachelor's degree in electrical engineering. During my schooling, I spent 2 summers here at Wurth, interning throughout the summer, and upon graduation, I accepted a full-time position at Wurth as a design engineer with a full-time start date in December of 2010. So about 10 and a half years now of design experience here at Wurth. I had been working as a full-time design engineer for several years, and in October of 2019, I took on the added responsibility as the UL engineering liaison. Today, my workload, I would say, is split about 50% of my time spent on new custom magnetic designs, and the other 50% devoted towards other UL-related topics. In this new role as a UL engineering liaison, I support our engineering and sales teams for all UL topics. That can range from anything from helping to interpret safety standards for our engineers to helping assist our customers to submit one of our custom transformers for a component level UL recognition. Of course, along with that responsibility comes the added responsibility of maintaining the UL test reports and coordinating with our factory teams for UL inspections and audits. So in today's presentation, I hope to share a balance from both of my current roles. I'll start with sharing some background information regarding some of the common safety standards that we design here at Wurth. We'll then transition into defining some of the common safety terms and terminology, and then, where do these come from and what do they mean? These various safety factors or terms can then influence the transformer in terms of size, cost, and performance, and so we'll go into a bit more detail on those. And then I'll show a couple of different common design techniques we use here at Wurth to meet these safety standards. And then finally, we'll take that design topic one step further, and we'll discuss how these design techniques will affect your transformer in terms of size, performance, and the always important topic of cost. At the end, there'll be some additional time for any questions that you may have. For anybody out there that doesn't want to have their question maybe read live, you can certainly send your questions into Amelia, and she'll make sure that they make their way to me. And then over the course of the next few days, I'll try to reach out directly to you and provide the best support that I can. So protecting the end user of electrical equipment against the risk of fire, electric shock, and injury is a very important aspect of transformer design. To be honest, that's why Wurth Elektronik Midcom is in business, to provide safety isolating transformers and to maybe take that part of the design out of the equation for you as maybe a system level design engineer. There's nearly an infinite number of safety standards written for various categories of equipment. Here at Wurth, we design our custom transformers to meet many different safety standards, with only a few of them listed here on the screen. As you can see, we design our custom transformers to meet anything from medical equipment to adjustable speed power drives that are often used in, say, the industrial marketplace, even household appliances, and pretty much everything in between. The technical committees that are responsible for writing each of these standards often refer back to multiple different base safety standards, if you will. This creates a fair amount of overlap between the various safety standards we design, at least in terms of the transformer construction. But there's also many subtle differences. In some cases, certain wire types are not allowed to touch one another. There might be different requirements for the number of thin sheet insulation, and so on. As you can imagine, the safety requirements for a life-sustaining medical device that could potentially be connected to an unconscious patient will be quite strict compared to, let's say, the safety requirements for laboratory equipment, where the end user of that laboratory equipment is typically a skilled and trained worker. Here at Wurth, we own corporate copies of most of these standards, and we reference them daily. We've also invited UL to our corporate headquarters here in Watertown on a number of different occasions to train our engineers on how to interpret these standards. So as you can see, we take the responsibility of safety very serious here at Wurth. When it comes to interpreting safety standards, our design engineers will need to be provided several pieces of information from our customers. These pieces of information include insulation grade, which is required by the end application, the overvoltage category, which refers to how the end application is connected to the mains, the pollution degree, or the environment that the end application will be exposed to, the highest possible altitude where the end application could operate, as well as the peak and RMS working voltages. These are really application dependent variables that we really need this information from our customers. This is not something that our engineers can calculate, or at worst, we don't want to be making assumptions at the front end of a design that could cost you later when you submit your full end application for UL or VDE approval. The first vital piece of information that our design team needs to know is the insulation grade required by the transformer. Keep in mind, this is not necessarily the same as the insulation grade required by the end application. In some cases, the end application might have several different avenues or means for meeting safety. You may have several maybe DC to DC transformers throughout the power supply. The external enclosure might be grounded, for example, and that provides a level of isolation. When we talk about insulation grades, there's several different grades of insulation to keep in mind. The first shown here on the screen is called functional insulation. Just like it sounds, functional insulation is only intended to offer insulation necessary for the proper functioning of the equipment. It's not intended to protect the end user from electric shock. The safety standards oftentimes don't require a certain distance to be maintained between the primary and secondary sides of the transformer. Usually the only requirement is maybe a low voltage dielectric test, just to make sure that maybe the primary and secondary are not shorted to one another. As we move up to the next level, known as basic insulation, there is now a certain level of protection against electric shock provided by basic insulation. I like to think of basic insulation as providing only one layer of protection. I guess for me, this is easy to remember because basic insulated wire that's used commonly throughout the industry only offers one layer of extruded insulation. Most standards require a specific distance to be maintained between the primary and secondary when designing for basic insulation. Typically, this falls in the range of, let's say, 2 to 4 millimeters for standard offline input applications. The dielectric requirements also tend to be in the range of that 1500 to 2500 volts AC. The next level up after basic insulation is supplementary insulation. The safety standards generally require the same 2 to 4 millimeters of distance between the primary and secondary. And the dielectric voltage is also generally in that same 1500 to 2500 volt range as is required with the basic insulation. The biggest difference here is that the standards will usually increase the amount of solid insulation that's required between the primary and secondary. This solid insulation can be met with maybe thicker bobbin plastic or increased layers of tape, or the more common method would be to use a supplementary insulated wire. Supplementary insulated wire actually has 2 layers of extruded insulation. So I show there on the screen, basic insulation with 1 layer, supplementary insulation with 2 layers. We typically only use supplementary insulation when there is another level of basic insulation provided somewhere else in the end application. The combination of basic insulation plus supplementary insulation is known as double insulation. The term double insulation just simply refers to having 2 separate and independent means of insulation. The supplementary insulation itself is just there to provide a second means of protection in case the basic insulation were to fail. I like to think of double insulation as providing the basic, or 1 layer, plus supplementary, or 2 layers, for a total of 3 layers of insulation. As we move to the last insulation grade, known as reinforced insulation, we see there on the screen that I also show 3 layers. This is probably the most common type of insulation that we design to meet here at Wurth. The key to the definition of reinforced insulation, however, is that reinforced insulation is a single insulation system that's applied to a live part, or a part that's connected to the mains hazardous voltage, which provides protection against electric shock that is equivalent to double insulation. Remember, as I said earlier, double insulation is made up of basic insulation, or 1 layer, plus supplementary insulation, or an independent 2 layers, for a total of 3 layers of insulation. Reinforced insulation, on the other hand, is often achieved by using a triple insulated wire on only one of the transformer windings. This triple insulated wire provides 3 layers of extruded insulation. So double and reinforced insulation both provide that 3 layers of insulation that we're looking for, but they do it in completely different manners. When we're talking about reinforced insulation, the safety standards generally require safety distances in that 4 to 6 millimeters, or maybe even 4 to 8 millimeters in some cases. And the dielectric requirement, generally 3000 volts to 5000 volts, depending on, again, other factors that we'll discuss later in the presentation. Shown here is just a basic diagram of all the possible layers of insulation that could be needed in a simplified end application. These various levels of insulation are labeled by the letters A through E, and some of the levels of insulation are quite easy to identify. The letter A, for example, would need to meet reinforced insulation in order to isolate this mains hazardous voltage from the outside enclosure that could potentially be touched by an end user. But some of the other levels of insulation, B, C, D, and E, are not quite that simple. Let's assume, for example, that you requested a new custom transformer from Wurth that's intended to step down this mains voltage to this 30-volt output. So the transformer you're looking for would be shown here in this red box, providing the level B isolation. But what does level B need to meet? Let's assume, for instance, that you request functional insulation only. What does that mean for the rest of the C, D, and E insulation levels? Well, in this case, the letter C would now also need to have reinforced insulation similar to level A in order to isolate the hazardous voltage from the outside enclosure to protect this end user once again. Likewise, the letter D would also need to have reinforced insulation. This is needed to protect the end user that's maybe using whatever end application is powered off this 10-volt output from the mains hazardous voltage as well. So now we have reinforced, reinforced, reinforced here on A, C, and D. That leaves letter E with only needing functional insulation because this letter D here is already providing the necessary reinforced insulation to protect this end user from any kind of hazardous voltage here that could be touched by the outside enclosure. But now let's go back and let's change that example. Let's suppose you ask for supplementary insulation at letter B. Letter C now becomes basic insulation only in order to provide supplementary plus basic for a total of double insulation to the outside enclosure to protect this end user. Likewise, letter D would also be basic insulation at minimum to have supplementary plus basic for double insulation protecting this end user. Letter E in this case stays as functional insulation, right? We already have our supplementary plus basic, so we only need functional insulation from this 10-volt to the outside enclosure to protect this end user. So as I said in the previous slide, the transformer insulation grade does not necessarily need to meet the exact same insulation grade of the entire end application. The next piece of information that's important for the Wurth engineers to know is the overvoltage category. The overvoltage categories are listed by Roman numerals 1 through 4. Quick examples of overvoltage categories are shown here in the figure, with overvoltage category 4 maybe being the electricity meter located outside of your house. Overvoltage category 3 would then maybe be light switches or your wall outlets inside your house. As we step over to overvoltage category 2, you're talking about pluggable equipment, maybe appliances throughout your house, your TV, your laptop, etc. And then overvoltage category 1 would be maybe a USB charger plugged into your laptop to power your cell phone. Most common type that we design here for at Wurth is the overvoltage category 2. However, we do occasionally see overvoltage category 3 requests for things like maybe smart metering applications or maybe industrial equipment that's hardwired directly into the building wiring. The important part here is that the higher the overvoltage category number, the higher transient overvoltage that can occur. This means that as we increase from overvoltage category 1 to 2 to 3 to 4, we must also increase the distance between the primary and secondary sides of the transformer. So the transformer typically must grow in size to provide these extra distances. Oftentimes, we also have to test at a higher dielectric test voltage to ensure that the insulation between the primary and secondary can now withstand these higher transient overvoltages. This might mean we need to add additional layers of tape or tubing or something along those lines to provide that higher dielectric constant between the primary and secondary. Adding these additional processes and materials is going to affect the cost of your transformer. The pollution degree is the next piece of information to understand. This is dictated by the pollutants possible in the environment where the end application will be operated. The pollution degrees are defined by numbers 1 through 4 as shown on the screen. Pollution degree 1 describes an environment free of conductive pollutants. This is very difficult to achieve. From the transformer perspective, it often means we need to vacuum pot the entire transformer to rid the inside of the coil even of any kind of air pockets or anything that could potentially be seen as a contaminant. Pollution degree 2 is the most common type of environment we design to meet here at Wurth. In the pollution degree 2 environment, only non-conductive pollution occurs with an occasional conductivity occurring due to condensation. Conductive pollution does occur, however, when we move up to pollution degree 3 environments. This type of environment typically has dry non-conductive pollution, which only becomes conductive due to condensation as well. We do see pollution degree 3 environments maybe in, say, an industrial application. The worst case environment is pollution degree 4. In this case, there's continuous conductivity, maybe due to conductive dust, rain, other wet conditions. Honestly, here at Wurth, I'm not aware of any transformers we've designed to meet pollution degree 4. My guess is that in those type of applications, we would probably look for a vacuum encapsulated type of solution to seal the entire transformer and aim for a pollution degree 1 environment, if at all possible. As you can imagine, as you increase the pollution degree, you're also increasing the likelihood of contaminants causing a conductive short between your primary and secondary side of the transformer. So the safety standards compensate by requiring greater and larger distances between the primary and secondary. Again, this increased isolation distance may result in a larger transformer, similar to the case with overvoltage categories. Likewise, increased conductive pollutants may mean that we have to test at a higher dielectric level. So again, we may need to have additional tape layers, tubing, and things of that nature. And again, those added materials and processes, they may affect your cost as well. Another environmental condition we must account for is the altitude in which the end application will be operated. Of course, as you increase altitude, the atmospheric pressure will decrease. This means that a dielectric breakdown or an electric arc is more likely to happen at a lower voltage because of the decreased atmospheric pressure. The safety standards again compensate for the lower atmospheric pressure by requiring larger distances to avoid this electric arc from occurring. They oftentimes also require a higher or increased dielectric voltage testing. Again, the larger distances means a possible larger transformer, so increased size, and the increased dielectric voltage could mean additional layers of tape and tubing, which can add to the cost of the transformer. The next safety input to understand is the working voltage. This is defined as the highest voltage across any insulation at the maximum rated input voltage and under normal operating conditions. The attached image here is taken from the VDE instruction on how to physically measure the working voltage. The worst case voltage in flyback applications is often present between the drain of the MOSFET and the secondary output diode. This is not always the case, but this is generally where VDE starts their measuring when they're doing an end application approval. This working voltage can sometimes be predicted with some level of accuracy by using various simulation tools or by calculation. As you can imagine, it's hard to define that working voltage at the very front end when you don't even have a transformer to do any testing on your power supply. The problem is that the working voltage can be influenced by parasitics such as leakage inductance, not only in the traces on your board, but also the leakage inductance in the transformer. The leakage inductance can be very challenging to predict and calculate. So it's best practice to add a bit of margin on top of any of the values that you find by simulation or calculation. In the end, the measured value that you see in your physical power supply can possibly be reduced by maybe adjusting the turns ratio to reduce the reflected voltage onto the primary, of course, maybe a reduction in leakage inductance, or even by applying a harder snubber circuit. The important point is if the measured working voltage is less than the highest rated mains input voltage, we must use the mains input voltage as our working voltage. Just like with the overvoltage categories and pollution degrees, as the working voltage increases, the separation distances required by the safety standards will also increase, which can lead to an increase in the size of the transformer. Likewise, the higher working voltage results in a higher dielectric test, which can lead to the need for additional tape and tubing that can add to the cost. Here at Wurth Elektronik, we have a handy one-page form that we'd like to use to capture all the transformer design critical parameters. At the very bottom of this form, there are lines for our customers to provide the safety standard, insulation grade, overvoltage category, pollution degree, and working voltage that we just discussed. I encourage you that if you have a need for a new custom transformer, to reach out to your local Wurth Elektronik sales representative to request one of these forms. So once we've captured all of these application-specific inputs, the Wurth design engineer will start their homework. They'll start digging into these safety standards, searching the tables throughout the relevant safety standards, and calculating the required safety distances that need to be maintained between the primary and secondary windings. These distances are split into two types: creepage and clearance. The creepage distances are defined as the shortest distance between two conductors measured along the surface of an insulating material. The clearance distance, on the other hand, is the shortest distance between two conductors, but this distance is measured through the air. Both the creepage and clearance distances are affected by insulation grade, overvoltage category, and pollution degree. The creepage distance, though, must be determined based on the RMS working voltage, while the clearance uses the peak working voltage. The figure on the right side of the screen here shows the creepage path in purple, while the clearance path is shown in blue. As you can imagine, it's not possible to have a creepage distance that is less than the clearance. The creepage path along a solid surface will always be the same or longer than the clearance distance through air. In some cases, the standards may have special requirements for the length of the gap that must be maintained in order for the creepage path to follow the insulating material. This is why you see in this top figure, the creepage path actually jumps across this gap, because this gap length is not long enough to be counted according to this particular safety standard. The Wurth design engineer will be responsible for determining the appropriate X dimension shown in this figure and ensuring that this does not affect the creepage distance on your transformer design. However, this X dimension may also be important for you to note if you plan to, let's say, cut a slot in your PCB to increase the creepage distance along the surface of your PCB. The last safety factor that must be considered is the material group or tracking index. This is a rating that is given to the insulating materials that are used. These ratings are given to everything from bobbin plastics to tapes to even the varnish that we use to dip our transformers in. The short version of the Cti Test Procedure is that two electrodes are placed 4 millimeters apart onto an insulating surface. The insulating material located between the electrodes is then subjected to a succession of drops of electrolyte solution until one of three things occurs. Either the overcurrent device operates, or a persistent flame occurs, or 50 drops of solution have been applied. The end goal of this testing is to determine the maximum voltage that can be applied between these two electrodes without resulting in either the overcurrent device operating or the persistent flame occurring. Oftentimes, the voltage potential applied between the electrodes will gradually create a conductive leakage path across the insulating surface. This leakage path will form a carbonized track, and this is what leads to the eventual failure of the insulating material during testing. Materials are rated using Roman numeral 1 through 3, as shown here in the table. Material group 1 rating shows that greater than 600 volts AC is applied between the two electrodes without either the overcurrent device tripping or a persistent flame occurring. As I move down the table to material group 2 and 3, you see that the test voltage must be decreased in order for the insulating material to pass this Cti test. This shows that Cti 1 or material group 1 is the best material available on the market. As I showed in the previous slide, the material group only influences the creepage distance. Well, keep in mind this makes sense because the creepage distance is the shortest distance along the insulating material, whereas clearance is the distance through air. So naturally, the insulating properties of the surface of the insulating material would not affect clearance. We've also talked about altitude, and altitude affecting the atmospheric pressure and thus the potential for an electric arc through air. Naturally, the altitude does not affect the creepage distance, but does affect the clearance. The difference with material group is that these are actually chosen by the Wurth design engineer based on the materials available on the market, whereas pollution degree, overvoltage category, working voltage, those are all dictated by the end application and the environment that the end application is operated in. As you can imagine, the better materials rated at material group 1 do tend to be more expensive, but they also lead to shorter safety distances required between the primary and secondary. We do have the capability here at Wurth to tool new components to ensure we can comply with the material group 1 requirements, but keep in mind that tooling can be expensive and can take more than 12 weeks to even provide the initial prototype samples. As we learned, the functional insulation grade does not provide any protection against electric shock. And there's often no creepage or clearance distances that must be maintained between the primary and secondary. For this reason, we consider functional insulated transformers as the best possible option in terms of size, performance, and cost. As we increase the insulation grade to basic, supplementary, and reinforced, we must start to utilize certain design techniques in order to comply with the safety standards. There's 3 main ways that we meet these various levels of insulation here at Wurth. The first is to use shelf or margin tape. A solution like that would look similar to the picture here on the left-hand side. The next option would be to use an extended rail bobbin, shown here by this middle picture. And the last option would be flying leads, as shown in the far right picture here, with the black wire sticking out from the side of the transformer itself. The first method is one in which we use tape to meet our necessary creepage and clearance distances. These blue X's shown here on the screen are intended to simulate multiple layers of tape stacked up along both sides of the winding area of the bobbin. This shelf tape will need to be the appropriate width to provide the full creepage and clearance distance between adjacent windings. The way this type of method works is for this first winding, we would first place the shelf tape along both bobbin flanges, wind the secondary winding between the shelf tape, and then cover this winding with a full width tape as shown here in yellow. We would then repeat this process for the next windings. The idea here is that the creepage path from, say, this first secondary to the next primary winding would then need to follow the surface of the tape, up the bobbin flange, and then back to the primary. As a reminder, basic and supplementary insulation typically requires 2 to 4 millimeters of creepage and clearance, while reinforced insulation is in the range of 4 to 6 or maybe even 4 to 8 millimeters. We need to make sure that this margin tape is the proper width on both sides of the bobbin to meet that full distance. If you see here on this top image, you'll notice how, say, the start D and the finish D winding here will actually cross this margin or this shelf tape. So if we envision this D winding being terminated on this side of the bobbin, the D winding lead wires, start D and finish D, would come down along the bobbin flange across the shelf tape and then be wound between the layers of shelf. Let's say that this next winding is now the E winding. The lead wires for the E winding on this secondary would come down this side across the shelf and be wound between the margin tape. So this shelf tape here in particular needs to provide the full creepage and clearance distance in order to isolate this winding across this shelf to where that lead wire came down. There's other ways to provide additional insulation, such as tubing or other tapes that we've talked about, but again, those will add further to the cost of the transformer. The next method involves the use of an extended rail bobbin. With this type of method, the bobbin itself is extended, typically only on one side, as shown in the red circle here. This type of method will use that basic supplementary or triple insulated extruded wire that we discussed several times earlier in the presentation. The idea is that the insulated wire is terminated to the extended rail side of the bobbin. The critical safety point on the insulated wire is this termination location where the extruded insulation is no longer present in order to create the solder joint here on the terminal. The extension of the bobbin will move these termination points away from the winding area where maybe the magnet wire on, say, your primary and aux windings are being placed inside. Another critical point of the extended rail bobbin is that we also have to keep the ferrite core in mind. So as you can imagine, there's going to be a couple of core halves sitting on the bobbin up here. These secondary terminations must also be the full creepage and clearance distance from that ferrite core. That ferrite core is treated as a dead metal short, and if we do not meet the full distance, we have the potential of a safety violation from the insulated termination to the core, and from the core back to the magnet wire terminations on the other side of the bobbin. The last method mentioned involves the use of flying leads. This is sort of a hybrid between the shelf tape and extended rail bobbin methods. In this case, we can use the smaller footprint bobbin that was used in the shelf tape method, but we no longer need these shelf or margin tapes along both sides of the bobbin. This allows us to use the full width of the winding area. This may seem like a great option at first, but this is the least preferred method by Wurth. As you can imagine, these flying leads that exit out the side of the bobbin are present early in the construction of the transformer process. There's potential for these leads to be, say, bent back and forth as they go through the remaining winding process, as they go through soldering, as they go through taping, as they go through testing, varnishing. And then of course these leads can be further damaged as you ship or as you insert these leads into your PCB at the PCB assembly process. And this just opens the door for some reliability and quality concerns later on in the life of the transformer. Certainly we can design in this type of manner, but we try to avoid it if at all possible. In this type of method, we would also use the special extruded insulation for these flying leads. The idea being that the end of the flying lead will be stripped and tinned, and then our creepage path from this critical location then follows the remaining extruded insulation back to the rest of the transformer, whether it's the core or the magnet wire terminations or the winding area. One important point to keep in mind is that these flying leads must be manually inserted in the PCB. This is a highly manual process and can add to the cost of your PCB assembly process. We typically use different wire types depending if we intend to meet safety using the shelf tape, extended rail, or flying lead methods, as I touched briefly on in the previous slides. Remember I mentioned in the shelf tape method, the tape itself is used to provide the necessary creepage and clearance distances. This means that each of the windings can use a standard enamel-coated magnet wire between these shelf tapes. This is similar with functional insulated transformers, where standard enamel-coated magnet wire is also used. As we move to the extended rail and flying lead methods, as I mentioned, we'll need to utilize a special insulated wire in order to provide the creepage and clearance distances. Basic insulation will require at a minimum a basic insulated wire, which, as I mentioned previously, provides one layer of extruded insulation. Supplementary insulation will then require supplementary insulated wire, which has 2 layers, and reinforced insulation grade will then require a triple insulated wire with 3 layers of extruded insulation. These special insulated wires have significantly larger wire diameter than the standard enamel-coated magnet wire that we would use on the shelf tape or functional designs. I show here on this slide that a basic insulated wire may be in the range of 15% larger diameter than the equivalent enamel-coated magnet wire. As we move up to supplementary wire, we're looking at maybe a 40% increase in the diameter. And then at triple insulated wire, we're talking possibly 65% larger diameter or more. These increases to the overall diameter will vary depending on which wire gauge we're talking about. As you can imagine, the outer insulation layer on the copper wire remains pretty consistent. So when we're talking about a 24 gauge enamel coated magnet wire versus a 40 gauge, that outside extruded insulation will be a larger percentage of the overall diameter with a smaller 40 gauge diameter type wire. As I said, a functional insulated transformer would use standard enamel coated wire on all windings with no shelf tape. When we increase the insulation grade and use shelf tape to meet safety, we'll now consume a large portion of the winding area with these shelf tapes. As I mentioned earlier, reinforced insulation, for example, could require 4 to 6 or 4 to 8 millimeters on both sides of this bobbin. It's easy to see how possibly 50% of my winding area on the bobbin could be consumed with just tape used to meet the safety. A winding that might fit in one layer, for example, on a functional insulated transformer, may now be forced into 2, 3, or 4 layers once I add the shelf tape. Having less total winding area and also consuming more area with the existing windings may force the Wurth design engineer to move up to the next size larger transformer. Again, we no longer have the shelf tape present on the flying lead or extended rail methods for meeting safety, but one of the windings, typically the secondary, will use this special insulated wire. As I mentioned on the previous slide, a reinforced insulated wire could have 65% larger diameter than its equivalent standard enamel coated magnet wire. So a 10-turn secondary using enamel magnet wire might fit in one layer, but a 10-turn secondary with 65% larger diameter may now be forced into 2, 3, or 4 layers. Similar to the shelf tape method, I effectively now have less winding area available on the bobbin to fit the necessary turns. This again can force the Wurth design engineer to have to use the next size larger package. Here I show a common EFD20 core shape. If we assume all windings for a shelf tape, flying lead, and extended rail design will fit on this EFD20 bobbin, we can see that the extended rail method is certainly the largest transformer in terms of the overall footprint consumed on the PCB. This is due to the fact, as I mentioned earlier, that the extended rail portion of the bobbin must provide the full safety distance. In the case of a basic insulated design, it may be 2 to 4 millimeters. In the case of a reinforced design, it could be 4, 6, or possibly even 8 millimeters. You'll notice that the height of the transformer is also increased compared to the shelf tape and flying lead designs. This goes back to the point where I mentioned that the insulated wire, particularly a reinforced insulated wire, could be 65% larger diameter. Because of that, we must now increase the height of these standoffs on the bottom of the bobbin to ensure that large diameter wire that's routed through these slots does not contact your PCB. I show a through-hole concept here, but keep in mind with a surface mount design, this would also be very critical. If the depth of this slot where the insulated wire would lie is not deep enough, there's potential that the insulated wire would rest on the PCB directly, and your pins of the transformer would now float off the PCB during the reflow process. When we start looking at how safety affects performance, leakage inductance is probably one of the biggest concerns. Here at Wurth, we design a lot of flyback transformers, and of course, flybacks and leakage are typically not two things we want in the same sentence. If you remembered earlier, I showed a figure of how VDE recommends to measure the working voltage across the drain of the MOSFET and the output diode. High leakage inductance can result in a large reflected voltage, resulting in a significant increase to the peak working voltage that's measured at the drain of the MOSFET. The figure in the top right corner, for example, shows a large voltage spike caused by high leakage inductance. If we, at the very beginning of your process, design for your nominal 50 volt input, but at the end, find that your input is actually 3 or possibly 4 times that 50 volt level, we may not meet your creepage clearance or dielectric requirements at the end of the day. When we look at the leakage inductance formula, there's 3 major factors that are affected when we design to meet safety. The first is the winding width, represented by the W here in the denominator of the formula. As I said, it's not surprising for a shelf tape method to have roughly 50% of the total winding area consumed by tape. This effectively cuts my overall winding width that's remaining on the bobbin in half, in turn doubling my leakage inductance. This winding width is not necessarily affected in the extended rail or flying leads because, as I mentioned, we're able to utilize the full width of the bobbin. However, the next critical factor in the leakage inductance formula is the mean length turn of the windings, represented by the MLT here in the numerator. We discussed how a 1-layer winding in a functional insulated design may now be forced into 2, 3, or possibly 4 layers in the case of a shelf tape, flying lead, or extended rail design. Of course, the additional layers of winding stacked on top of one another will increase the mean length turn, effectively increasing my leakage inductance. The last critical factor is the insulation thickness, represented by the letter T in the numerator. A shelf tape design, as I said, will use a standard enamel-coated magnet wire similar to a functional insulated design. In this case, both the functional insulated and shelf tape designs will have similar thickness of enamel coating and generally the same thickness of tape between adjacent windings. So the insulation thickness variable is not necessarily a big factor in shelf tape designs. However, the special insulated wire used on flying lead and extended rail designs, as I mentioned, could be, say, 65% larger diameter for a reinforced wire than the comparable enamel-coated magnet wire. All this diameter increase is from the extra extruded insulation on the outside of the copper wire. This insulation will force the primary and secondary windings further apart from one another, increasing the total thickness of the insulation, in turn, increasing my leakage inductance. Again, an increase in leakage inductance can mean an increase in the measured working voltage. A larger working voltage may require larger creepage distances to be maintained between the primary and secondary wires. So this leakage inductance topic is not necessarily just a loss that you see in the performance side of things, but it can also have a huge impact or effect on the size of the transformer. I've already alluded to the fact that shelf tape and insulated wire will consume a large portion of the winding area on the bobbin itself. And oftentimes this forces the Wurth design engineer to have to use the next larger transformer package size to fit all of the windings. But what happens in the case where you don't have this room or this footprint available on your PCB in the end application? An alternative option is to simply reduce the wire diameter of the copper wire to help fit all the windings on this smaller package size. The trade-off here is, of course, a higher DC resistance and typically higher temperature rise that you'll see in your end application. Another possible solution could be to maybe remove some turns off of the transformer. The outcome there is now you're driving the core harder, you're increasing your flux density of the core, and you're going to see increased core losses and increased temperature rise in the core as well. One of the most important factors to consider is always cost. We've already discussed how the use of margin tape and special insulated wire can force the Wurth design engineer to utilize a larger package size in order to fit all the windings. Naturally, as you increase the size of the bobbin and the size of the ferrite core, you're going to use more ferrite and more bobbin plastic, so the larger components are going to cost more. The functional designs and shelf tape designs will use standard magnet wire. Standard magnet wire is costed by the weight of copper used. As you can imagine, the weight of copper on a 1-inch cube transformer is quite small, so the copper weight will also be quite small. The flying lead and extended rail designs, on the other hand, use this special extruded insulated wire, and this wire is costed by the length of wire used. It might seem insignificant on a 1-inch cube transformer, but it doesn't take many turns to achieve 1 meter worth of insulated wire on a 1-inch cube transformer. This 1 meter worth of insulated wire can easily be 5 times or more the cost of the equivalent magnet wire used on a shelf tape or functional insulated design. This is why you'll see in most cases on extended rail and flying lead designs, we'll use the insulated wire on the secondary winding only. As you can imagine, in an offline input application, the turns ratio will be in such a way that the secondary winding will have the lowest turn count. We utilize this large diameter insulated wire on the lowest turn count, 1, to limit the amount of room that's consumed on the bobbin by the large diameter wire, and 2, to try to have the shortest length of wire as possible to minimize the cost increase. Of course, on the shelf tape method, we must also take into account the material cost of the shelf tape used to provide the creepage and clearance distances. Tape itself is a rather inexpensive material, but keep in mind that it must be stacked at the same height as the winding in order for it to be effective as an insulation barrier. The tape itself is significantly thinner than the diameter of the magnet wire winding, so you'll often see that we use 10 or 20 layers of tape on each side of the bobbin. A standard flyback design often has 4 total windings, which means 8 margin tape operations, each having 10 to 20 layers of tape. This tape component cost can quickly add up. So how do these different materials and design techniques affect our production costs? Standard magnet wire used on the functional insulated and shelf tape designs can typically be automatically wound and automatically terminated. The machines intended to do these processes are usually fitted with several arbors, allowing us to wind 10 or 12 parts at one time. The extruded insulation, on the other hand, is a bit more difficult to terminate, which typically requires a single arbor machine winding 1 part at a time. This creates a high-cost bottleneck in the production process. Likewise, the magnet wire can often be directly soldered as well. The high-temp lead-free solder quickly eliminates the enamel coating and creates a quality solder joint on the bobbin terminal. The extruded insulation is different in the fact that it generally cannot be directly soldered without first stripping the insulation off the wire and then manually terminating the winding. There are some solderable extruded insulated wires on the market, but it's easy for these extruded insulated wires to be thinned or cracked or deformed when they're exposed to the high temp solder. Remember, the intention of the extended rail bobbin is for this extension to provide the full creepage and clearance distance from the termination to the windings inside the winding area of the bobbin. Damage that occurs along this insulated wire can violate this creepage and clearance distance if it's not well controlled. The shelf tape and extended rail methods of meeting safety will have all the windings terminated to a bobbin terminal and then soldered. The flying lead method, on the other hand, will have a defined length of flying lead that must protrude off the side of the transformer itself. This requires additional processes in production to cut the flying leads to length, to strip the insulation off the end of the wire, and then, of course, to avoid any corrosion on this wire during transport or storage, we must also tin the end of the wires as well. This involves several manual labor processes to ensure a high quality transformer is provided to you, the end customer. But these are also slow manual labor processes that create additional bottlenecks in our production facility. So up until now, the shelf tape method seems like the best method. We use standard magnet wire from the cheaper component cost. We can auto wind and auto terminate, but we also have to keep the application of the shelf tape itself in mind. As I mentioned, this shelf tape must be applied on each side of the bobbin, and a standard flyback typically has 4 windings. So you're talking 8 taping applications. There are cases where we have equipment that can apply this tape automatically, but once you get to winding number 2, 3, and 4, you're now applying this shelf tape over the top of the previous lead wires. This can create inconsistent areas for that shelf tape to lie and can make consistent automation nearly impossible. This means additional operators are needed in production to manually apply the shelf tape. And as we discussed, this can easily be 10 or 20 layers of shelf tape on each side of the bobbin for each winding. This creates more bottlenecks in production that would not be present on a functional design, or the flying lead or extended rail designs. So again, this can add to additional cost to your transformer. So that concludes my presentation for the day. Again, I appreciate everyone taking time out of their busy schedules. I'd like to leave a few minutes here now for anybody that may have any questions.
All right, our first question here. He says it's a little bit off topic. That's okay. Do you also offer custom design service of planar transformers based on PCBs and planar cores?
Sure, that's a great question. On our website, we do have a series of planar transformers that we do offer. Currently today, we do not pursue new custom designs of planar magnetics, but there are, like I said, a number of different planar magnetics available on our website that could potentially be used for you, and if the turns ratios, inductance, etc., are right for your end application. So I encourage you to go out to our website, take a look, see what we have to offer.
Absolutely. Yes, you can find our custom finish magnetics online at www.we-online.com, and then simply click on custom transformers. There you will see our custom packages and our finished magnetic components. Our next question here, also a good one. How do I get started on ordering a custom transformer?
Sure, that's a great question. I did mention earlier in my presentation that we have a one-page handy tool that I like to call it the power inquiry form. So what I recommend you to do is to reach out to your local sales representative, Wurth Elektronik sales representative, and request one of these power inquiry forms. It has areas for you to fill in things such as your input voltage, what secondary output voltage and current do you need. And then, of course, at the bottom of the form, there's also the area available for all of the safety critical information that is important for our design engineers to really tailor that custom design for your end application.
Excellent. Yeah, you can fill out the custom inquiry form, and if you can't find that, or if you want an easier route, you can simply reply back to our emails and we will get you set on the right track. Looks like our last question that's coming in, second to last question, I suppose. Are you able to give us some examples of some of the insulation grades?
So as I alluded to, there's really 4 or 5 main types of insulation grades, right? You talk about functional insulation. That functional insulation is not intended to provide any protection against electric shock. As we move up to, say, basic and supplementary insulated designs, those are really common in, say, the telecom boom back in the day. We've got a number of transformers that we sell that are catalog type transformers through the Wurth Elektronik Midcom brand name that were intended for that telecom industry. As you now move up to the double and reinforced insulated designs, you start to see a lot more of these offline type of applications. So laptop chargers, cell phone chargers, household appliances, like I said, industrial marketplace type applications is really where those reinforced type of designs are required in order to provide that full level of reinforced insulation for the end user. I'm not sure if that exactly answers your question. If not, like I said, feel free to send your question to Amelia. She can get that over to me, and we can discuss further if needed.
Absolutely. And then here we go, our final question coming in. And again, if you guys don't get your questions answered, don't worry about it, because we will make sure that we answer them later on through email or phone call. You can set up a Zoom meeting with us. We're everywhere. Our final question, do you have any examples for typical applications of pollution degree 2 and pollution degree 3?
Sure. So, like I said, pollution degree 2 is what we typically design to meet here at Wurth. That's anything like I said, a laptop charger, your household appliances, your standard office type environment, if you will. The majority of the pollution degree 3 type of designs that we see here at Wurth are, let's say, an industrial application where there could be a lot of dust or contaminants or that type of stuff within that environment. If you have some external fans, for example, to help cool the power supply itself, that those external fans can grab some of those pollutants and force them into the power supply. So we have to account for those types of pollutants in a pollution degree 3 type of environment. That's why the safety standards then require the larger safety creepage and clearance distances.
All right. Well, thank you very much, Landon, for presenting today. And thank you, everyone, for joining us for today's Wurth Elektronik webinar. Don't forget, next week, we do have 2 webinars coming up. We have our next power webinar. This is a joint presentation with ST Microelectronics, and it's migration to USB-C. And that's on Tuesday. Then on Wednesday, Frank Puhani returns with a behind-the-scenes look at current sense resistors. Register online at www.we-online.com/webinars. Hopefully, I am back in the office next week. Wish me luck with that. If you want to stay up to date with all of our webinars, you can always follow me on LinkedIn. My name is Amelia Thompson. You can also follow our corporate pages, Wurth Elektroniks on LinkedIn. And don't forget to check out our new podcast as well, the Wurth Elektronik What's Up Radio podcast. I hope everybody has a great day. I'll see you next week.